When three tropical cyclones spin across the Pacific Ocean on a single morning in late July, the headline always writes itself. It looks like a pattern. It looks coordinated. From the southern coast of China to the waters off Hawaii and down into the deep tropical waters off Mexico, three separate storms, Typhoon N, Hurricane Fausto, and Hurricane Genevieve, were turning simultaneously across 8,500 kilometers of open ocean. That is a span wider than the entire planet straight through its core, covering a third of the globe. But if you treat those three storms as three separate dramatic stories, or worse, as proof of some artificial manipulation, you miss the actual mechanism driving the entire hemisphere. The three systems never touched. They never steered each other. There was no physical connection between the storm making landfall near Hong Kong and the Category 2 hurricane bearing down on the Central Pacific. Instead, those three storms were simply three simultaneous readings taken off a single heat engine sitting in the equatorial ocean. The headline sells the dramatic image of a world spinning out of control. The reality is far more specific and infinitely more unsettling. Between late 2025 and mid-2026, the Oceanic Index tracking sea surface temperature anomalies in the central equatorial Pacific didn't just drift, it flipped. It underwent a massive shift of more than 1.5 degrees of anomaly across 5 consecutive measurement periods. The raw surface water didn't warm slightly. It jumped from below 26 degrees to over 28.7 degrees Celsius. The ocean flipped state from a cool La Niña into a rapidly intensifying classic El Niño configuration. And that simple numerical shift in the water completely alters where tropical storms are born across the largest ocean on Earth. To understand what this means for the immediate future, you have to look at the exact mechanics of how this ocean engine operates, why the real danger isn't where you think it is, and what specific indicators will tell us if this warming cycle is about to trigger a historic shift toward normally quiet coastlines. To grasp the true scale of what occurred on that single morning, you have to follow the first signal where it actually made landfall. At exactly 3:50 in the morning local time, Typhoon N struck the coastline of southern China near Qinghai in Guangdong province. It carried sustained winds of 162 kilometers per hour, a solid Category 2 equivalent, making it the strongest typhoon to hit the Chinese mainland in all of 2026. Striking at nearly 4 in the morning represents the absolute worst operational timing for any coastal population. In total darkness, emergency crews are blind, non-evacuated residents are sleeping, and the peak storm surge hits before the first light of day allows anyone to assess the damage. Ahead of landfall, forecasters issued warnings for up to 600 millimeters of rain, 2 feet of water falling onto saturated soil already being whipped by destructive winds. In Hong Kong, just 80 kilometers to the southwest, the observatory logged over 100 fallen trees, structural collapses on high-rise scaffolding, and more than 350 canceled flights, despite the storm center passing 50 kilometers away. But the damage in Hong Kong was merely a side effect of a much larger atmospheric system that had assembled itself with terrifying speed over the warm waters of the South China Sea. What makes Typhoon N critically important to the larger Pacific picture is not just where it ended up, but where it came from. 2 days prior, the system had crossed the northern end of Luzon in the Philippines as a much weaker severe tropical storm. When a tropical cyclone grinds over the rugged mountain ranges of an island like Luzon, the elevation physically disrupts the low-level circulation, stripping the storm of its tight structure. But as the air is forced up those slopes, it dumps vast amounts of water, causing catastrophic inland flooding. In the Philippines, the system claimed 3 lives and forced emergency crews to execute daring flood rescues hundreds of kilometers south of the track. Yet once that weakened vortex cleared the landmass and entered the northeast section of the South China Sea, it encountered an ocean surface that was running exceptionally hot, with virtually no upper-level wind shear to tear it apart. In less than 36 hours, an engine that had been battered by the mountains of Luzon sucked up the massive heat content of the upper ocean, reorganized its core, and transformed into a 162 km/h monster before slamming into Guangdong. As the storm closed in on the Chinese mainland, a striking discrepancy emerged in the official figures that quickly fueled online speculation. Early reports on the 25th of July placed the total number of evacuated residents in Guangdong at roughly 20,000. By the 26th, that figure had jumped to 340,000, and within hours, state media updated the tally to over 700,000 people moved out of harm's way. To a casual observer, a 35-fold increase in 24 hours looks like a cover-up or gross administrative failure. In reality, it demonstrates the cold, rolling math of disaster management. An emergency bureau cannot evacuate 750,000 people at 48 hours out. The forecast cone is too wide, and doing so paralyzes the transport network. As the track narrows, the orders expand out from vulnerable fishing villages to entire urban districts, moving in tandem with the sharpening forecast. That massive logistical effort is precisely why the casualties in China remained remarkably light given the wind speed. But while Asia was deploying its deeply entrenched typhoon infrastructure to absorb the impact of N, 5,000 miles to the east, a completely different system was behaving in a way that threatened a population with far less experience handling direct hits. While Typhoon N was tearing through Guangdong, Hurricane Fausto was spinning across the central Pacific with sustained winds of 160 kilometers per hour, a solid Category 2 storm. Located 1,060 kilometers southeast of Hilo on the Big Island of Hawaii, Fausto was tracking west at 21 kilometers per hour. Its hurricane-force wind core was relatively compact, stretching 80 kilometers outward from the eye, but its tropical storm-force wind field extended more than 295 kilometers. This distinction is vital for island geography. A storm does not need to execute a direct hit for its outer envelope to cripple an isolated archipelago. Over a 72-hour window, forecasters at the Central Pacific Hurricane Center issued 3 distinct assessments. First, warning of rising risks to land, then lowering the wind threat, and finally shifting the predicted track north of Oahu as a weakening 72-kilometer-per-hour tropical storm. This shifting trajectory wasn't a failure of meteorology. It was the physics of atmospheric steering in action. A massive subtropical high-pressure ridge sitting to the north acts as a wall, steering the storm westward. As that ridge nudges or weakens slightly, the storm finds the atmospheric gap, sliding poleward into cooler water and higher wind shear, which rapidly degrades its intensity. Yet, even as Fausto's predicted center shifted away from a direct land impact, safety agencies across Hawaii extended high surf warnings. This highlights a fundamental law of ocean storms. The center of a tropical cyclone is its smallest component, but its energy footprint stretches across thousands of kilometers of open water. As a hurricane churns the sea, it generates short-period, chaotic wind waves. As those waves travel away from the core, the ocean acts as a mechanical filter, sorting them by wavelength into long-period swells that can travel across open ocean with almost zero energy loss. When a 20-second period swell hits a shallow volcanic reef, it doesn't just create large waves, it forces immense volumes of water over the structure that must immediately drain back out to sea, creating lethal rip currents under bright, clear skies. For an isolated island state thousands of kilometers from any continental support, even a distant, weakening storm that delivers heavy swell and outer rain bands poses a severe operational test. And sitting 3,000 miles behind Fausto was a third storm, Hurricane Genevieve, which had just executed a rare and fully forecast rapid intensification cycle off the coast of Mexico, exploding from a modest tropical storm into a major hurricane in under 24 hours. The simultaneous appearance of these 3 systems across 8,500 miles of ocean brings us directly to the central mechanism that governs the entire Pacific. A warmer ocean surface does not simply create more storms out of thin air. The historical count of global tropical cyclones remains surprisingly stable over time. What changes drastically during a strong oceanic warming event is the birthplace of those storms. Under normal conditions, the Central Pacific features cool surface waters and strong vertical wind shear, acting as a massive graveyard that destroys tropical systems moving in from the east long before they reach Hawaii. But when the central equatorial Pacific warms rapidly, as it did between late 2025 and mid-2026, that atmospheric wall breaks down. The location where storms are born shifts hundreds of kilometers eastward into open, deep water. Instead of dying out, systems like Fausto and Genevieve find a continuous corridor of high ocean heat content and low wind shear, transforming a quiet oceanic graveyard into an open highway aimed straight at vulnerable targets. To know whether this current cycle will escalate into one of the most extreme Pacific seasons on record, there are 3 specific, verifiable indicators to monitor over the coming weeks. First, watch the Oceanic Niño Index updates issued by atmospheric agencies. If the sea surface temperature anomaly in the Central Pacific box breaches the plus 1.5 degrees Celsius threshold, the ocean engine enters Super El Niño territory. Second, monitor the track of Hurricane Genevieve and subsequent eastern Pacific formations. If these systems maintain their structural integrity past 140 degrees west longitude without rapidly decaying, the Central Pacific corridor is fully open. Third, watch for formal tropical storm watches or advisories issued for the Hawaiian Islands by the Central Pacific Hurricane Center. Until those specific thresholds are crossed, the Pacific remains in a state of high atmospheric tension, an engine fully spun up, waiting for the next spark. A single numerical reading from a floating buoy moored off the equator, plus 0.98 degrees Celsius above baseline, is currently dictating the path of storm systems across 8,000 kilometers of ocean. To understand why 3 separate tropical cyclones turning at once across the Pacific is not a random coincidence, you have to look at how this maritime baseline was established, how it behaved historically, and what happens when the natural oscillation flips on a continental scale. For decades, meteorologists at Environment and Climate Change Canada, alongside atmospheric scientists at the Canadian Hazards Information Service, have tracked these oceanic oscillations because the thermal state of the tropical Pacific acts as the primary atmospheric engine for weather extremes across all of North America. When the equatorial ocean warms or cools, it doesn't just alter local currents. It shifts the jet stream thousands of kilometers to the north, directly dictating whether Western Canada faces severe winter droughts, whether British Columbia's river valleys get battered by atmospheric rivers, or whether dry forest beds ignite across northern Alberta and Saskatchewan. The baseline system we rely on today to measure this oceanic engine was established in the mid-20th century through a global network of deep ocean buoys, satellite altimeters, and sea surface thermal monitoring stations. Scientists isolated a specific rectangular zone of the equatorial ocean, known as the Niño 3.4 region, a stretch of open water spanning from 120 to 170 degrees west longitude along the equator. The sea surface temperature anomaly inside this specific box forms the core of the Oceanic Niño Index. Under normal non-El Niño conditions, strong trade winds blow continuously from east to west across the tropical Pacific. These winds drag warm surface water westward toward Australasia, piling up heat in the western Pacific while pulling cold, nutrient-rich water up from the deep ocean along the coast of South America. This temperature gradient establishes what climatologists call the Walker circulation, a massive atmospheric loop where warm air rises in the west, travels eastward high in the troposphere, sinks over the cool eastern Pacific, and returns westward along the ocean's surface. For generations, this circulation pattern served as the steady baseline against which seasonal weather was planned. Under this historical baseline, the Pacific behaved within predictable limits. When the trade winds blew with exceptional strength, cold water dominated the equatorial belt, locking the ocean into a La Niña pattern. During La Niña phases, sea surface temperature anomalies in the Niño 3.4 box dropped below -0.5 degrees Celsius. For Canadians, a La Niña baseline historically meant colder winters across the prairies, heavy snowpack across the coast mountains of British Columbia, and relatively cool, stable conditions across the eastern Pacific storm corridors. Conversely, when trade winds slackened, the accumulated warm water slid back eastward toward the Americas, triggering an El Niño phase where anomalies rose above plus 0.5 degrees Celsius. In the historic record, extreme El Niño events occurred sparingly, most notably in 1982, 83, and again during the historic 1997-98 event. During those peak years, sea surface temperatures in the equatorial Pacific breached record thresholds, disrupting global fisheries, shifting storm tracks, and delivering unseasonably mild winters to Canada, alongside intense atmospheric river events along the Pacific Northwest. The baseline design assumption held by meteorologists was that the Pacific Ocean would quietly oscillate between these two states every 3 to 7 years, spending significant time in a neutral middle ground. Infrastructure across North America was engineered around this predictable range. BC Hydro designed its reservoir storage capacities along the Columbia and Peace River basins based on historical precipitation curves dictated by this oscillation. Emergency management agencies across Canada calibrated their seasonal flood and wildland fire preparedness cycles against these standard oceanic phases. But what occurred between late 2025 and mid-2026 stripped away that historic baseline entirely. In the November to January period of 2025, the Oceanic Niño Index sat firmly in La Niña territory at minus 0.54 degrees Celsius. The ocean was cool, structured, and operating within its traditional parameters. Yet in a span of just 5 overlapping 3-month periods, that index rocketed upward to plus 0.98 degrees Celsius, a massive thermal jump of over 1.5 degrees of anomaly. Raw surface temperatures inside the monitoring box climbed from 25.97 degrees to 28.71 degrees Celsius. This rapid flip from a La Niña state to an escalating strong El Niño represents a profound surge of energy injected into the global atmosphere. To put a thermal shift of 1.5 degrees Celsius across millions of square kilometers of deep ocean into perspective, consider the sheer volume of water involved. The Niño 3.4 monitoring region alone covers roughly 11 million square kilometers of ocean surface. Warming that volume of water by over 1.5 degrees requires an amount of heat energy millions of times greater than the total annual energy consumption of all Canadian households combined. It is not merely a surface skin of warm water, it is a thermal battery hundreds of meters deep that unplugs the normal atmospheric circulation and forces the global jet stream to reroute itself around a massive plume of rising heat. When the tropical ocean undergoes a thermal flip of this magnitude, it fundamentally alters the physics of storm generation across the entire northern hemisphere. Tropical cyclones require 2 core elements to survive and intensify: sea surface temperatures above 26.5 degrees Celsius to supply latent heat, and low vertical wind shear so the storm's vertical eye wall isn't sheared apart as it climbs into the upper atmosphere. Under the old La Niña baseline, strong upper-level winds across the central Pacific created high vertical shear, effectively acting as an atmospheric wall that sliced the tops off developing storms before they could move west toward isolated island chains like Hawaii. But as the current El Niño engine accelerates toward what forecasters now calculate as an 81% probability of becoming a historic top-tier event before the end of the year, that protective atmospheric wall completely vanishes. The wind shear drops, deep warm water stacks up thousands of kilometers further east, and storm birthplaces shift directly into regions that historically saw almost zero tropical activity. This structural shift in the baseline ocean state is why the events of July 2026 cannot be analyzed through the lens of individual weather stories. The traditional design assumptions built into emergency planning frameworks across North America were formulated around an ocean that spent most of its time sitting in neutral or weak states. Today, the equatorial Pacific is operating outside those historic boundaries, generating a continuous corridor of storm-ready ocean that spans across more longitude than exists between any 2 points on land. To understand how this changed baseline directly translates into real-world impacts on coastal infrastructure, warning systems, and transboundary water networks, we must look at the exact mechanical process that converts ocean heat content into destructive kinetic energy. That mechanism, and the physical indicators that show where this system will strike next, form the foundation of how forecasters track the gathering threat. A single sea surface temperature reading of 28.71 degrees Celsius in a remote rectangle of equatorial Pacific water is currently rewriting the operational physics for weather forecasters across North America. The common narrative suggests that a warmer ocean simply creates more hurricanes, but that headline framing is completely wrong and misses the far more dangerous reality. A warmer Pacific Ocean does not significantly increase the total annual count of tropical storms across the globe. What it actually does is far more sinister. It fundamentally alters the physical mechanism of where those storms are born, how fast they intensify, and how far eastward across the planet they can travel before dying. The true engine driving this phenomenon isn't just warm water on the surface. It is the thermodynamic stack known as ocean heat content, combined with a sudden collapsing of upper-level wind shear across thousands of kilometers of open ocean. To understand how this heat engine physically operates, you have to look at how a tropical cyclone functions at a molecular level. A tropical storm is essentially a massive thermodynamic engine that runs on latent heat. Warm surface ocean water, anything above 26.5 degrees Celsius, evaporates rapidly into the low-level air mass resting directly above the ocean floor. As this hot, moisture-laden air rises into the atmosphere, it cools and condenses into thunderclouds, releasing immense quantities of latent heat energy into the middle atmosphere. This release of heat causes the surrounding air to expand and warm further, lowering the barometric surface pressure at the center of the storm. Lower surface pressure acts like an atmospheric vacuum, accelerating surrounding surface winds inward toward the center. Those faster winds churn the sea surface even harder, accelerating evaporation, releasing even more latent heat, and locking the storm into a runaway, self-reinforcing feedback loop. In a normal oceanic state, two natural braking mechanisms prevent most storms from exploding into runaway superstorms. The first brake is ocean churn. As a hurricane's powerful surface winds spin over the water, they violently drag up cooler water from depths of 50 to 100 meters below the surface. If that cold water layer is close to the surface, the storm effectively strangles itself by upwelling cold water into its own fuel intake, killing the feedback loop. The second brake is vertical wind shear, strong, high-altitude winds blowing in a different direction or at a different speed than the surface winds. High shear physically tilts the vertical column of the thunderstorm, venting the concentrated heat column sideways into the surrounding atmosphere and blowing dry air directly into the storm's core. Under normal baseline conditions across the central Pacific, high wind shear acts as an invisible shield, chopping the tops off developing tropical depressions long before they can reach isolated target areas like Hawaii or threaten atmospheric transport routes heading toward the Pacific coast of North America. During a rapid El Niño shift like the one recorded between late 2025 and mid-2026, both natural braking systems break down simultaneously. As trade winds collapse, a deep layer of warm water, often extending more than 100 meters below the surface, stacks up across the central and eastern Pacific. When a storm churns the water beneath it, it no longer pulls up cold water. It upwells more warm water, keeping the thermodynamic engine firing at full throttle. Simultaneously, the large-scale atmospheric circulation shifts, dropping vertical wind shear across the equatorial belt to near zero levels. Without wind shear to tilt the storm or cold upwelling water to choke it, the feedback loop runs entirely unchecked. This physical state is what enables the phenomenon known as rapid intensification, where a system's maximum sustained winds jump by more than 55 kilometers per hour in a single 24-hour period, exactly as Hurricane Genevieve did off the coast of Mexico. This mechanical breakdown was detected directly by an array of high-precision oceanographic monitoring instruments. Ocean Networks Canada, tracking deep-sea temperature and current profile data off Vancouver Island, alongside satellite altimeters operated by international space agencies and the Canadian Hazards Information Service, logged a massive shift in ocean surface topography and subsurface heat content. Automated drifting buoys deployed throughout the equatorial Pacific measured surface temperatures climbing past 28 degrees Celsius, while underwater Argo floats revealed that the 26-degree thermal threshold had dropped to unprecedented depths. The standard predictive models relied upon by agencies like the Canadian Hurricane Center in Dartmouth were built on historical datasets where deep ocean heat content was concentrated almost exclusively in the far western Pacific. When those algorithms encountered an ocean where deep heat content had shifted thousands of kilometers eastward, traditional intensity forecasts failed to capture how rapidly these storms could scale up. The breaking point of this system is that it completely redefines regional exposure. When the birthplace of tropical cyclones shifts eastward into the central Pacific, systems no longer have to cross thousands of kilometers of open, cool water to reach previously isolated landmasses or affect North American climate patterns. Instead of dying off over open water, these storms remain fully intact, maintaining tropical storm force wind radii exceeding 300 kilometers and pushing powerful, long-period swells across entire ocean basins. To know whether this thermal feedback loop will escalate further as we approach the seasonal peak, we must look at the specific operational metrics being recorded at monitoring stations across the continent. Those physical indicators, and what they reveal about the immediate future of coastal preparedness, will determine how this unprecedented ocean flip ultimately resolves. When a deep ocean heat engine flips state across 8,000 kilometers of open Pacific water, the real impact isn't just felt on distant tropical islands. It translates directly into real-world consequences for critical infrastructure, supply chains, and emergency preparedness networks right here in Canada. To understand how a numerical anomaly of plus 0.98 degrees Celsius along the equator alters daily life in North America, you have to follow the atmospheric chain reaction from the open ocean straight into our mountain passes, shipping corridors, and municipal power grids. The jet stream, energized by the massive release of latent heat in the equatorial zone, shifts its northern branch, driving high-amplitude weather patterns that bring compound hazards across the continent. When the ocean engine accelerates, the weather systems reaching British Columbia, Alberta, and the Atlantic coast no longer conform to traditional historical baselines, forcing transportation authorities and emergency management agencies to adapt in real time. Consider what happens along Canada's Pacific trade corridors when tropical energy alters atmospheric circulation. The Port of Vancouver handles over 140 million tons of cargo annually, acting as the primary marine gateway connecting Canadian producers to Asian markets. When atmospheric river events, fed by deep tropical moisture corridors originating near the equator, slam into the coast mountains of British Columbia, the resulting precipitation doesn't just flood local river basins. It triggers catastrophic landslides that sever critical transport infrastructure. We saw this exact vulnerability exposed in November 2021, when a series of atmospheric rivers dropped over 300 millimeters of rain across southern BC, severing every major rail line and highway connecting the Port of Vancouver to the rest of Canada. A single week of severed transcontinental rail lines stranded thousands of shipping containers, choked off grain exports from the prairies, and disrupted supply chains nationwide, costing the national economy billions of dollars. The impact extends far beyond coastal transportation hubs and deep into our inland water management systems. In Western Canada, reservoirs like Lake Diefenbaker on the South Saskatchewan River System and BC Hydro's massive Williston Lake behind the WAC Bennett Dam are calibrated around predictable seasonal snowpack and glacier melt from the Columbia Icefield and Athabasca Glacier. When an aggressive El Niño phase alters winter jet stream trajectories, it delivers warmer, drier conditions across the prairies and southern interior, drastically reducing winter snowpack accumulation. A multi-year deficit in alpine snowpack translates directly into dropping reservoir levels, threatening municipal water supplies for cities like Calgary and Edmonton, restricting agricultural irrigation across southern Alberta and Saskatchewan, and forcing hydroelectric utilities to manage reduced generation capacity. When Lake Diefenbaker drops toward critical intake elevations, water allocations governed under transboundary agreements become severely strained, demonstrating how an ocean thermal shift thousands of kilometers away dictates municipal water security. At the same time, shifting atmospheric circulation patterns exacerbate extreme wildfire risk across the Canadian boreal forest. The 2023 wildland fire season was the worst in recorded national history, scorching over 15 million hectares of land, an area larger than the entire province of Nova Scotia and New Brunswick combined. When an escalating El Niño pushes warm, dry air masses northward during the spring and summer months, it creates long-lasting high-pressure ridges that dry out forest fuel beds weeks ahead of schedule. The Canadian Wildland Fire Information System, monitored by Natural Resources Canada, tracks fuel moisture codes across millions of square kilometers of timber. When those indices spike, a single lightning strike can ignite uncontrollable fire fronts that threaten remote industrial towns like Fort McMurray, devastate iconic national parks like Jasper, or trigger mass evacuations that overwhelm provincial emergency alert systems like Public Safety Canada's Alert Ready framework. Even along Canada's eastern seaboard, the transcontinental atmospheric reach of a major Pacific Ocean shift is felt directly. The Canadian Hurricane Center in Dartmouth closely tracks how global atmospheric shifts alter Atlantic storm activity. While El Niño conditions historically increase vertical wind shear across the Caribbean, the simultaneous warming of Atlantic sea surface temperatures creates a hyper-complex forecasting environment. When post-tropical or tropical systems transition into high-latitude environments, as Hurricane Fiona did in September 2022, the damage to coastal infrastructure is immense. Fiona struck Atlantic Canada with a record-low barometric pressure of 931.6 millibars, washing away coastal homes in Port-aux-Basques, destroying harbor infrastructure across Prince Edward Island, and leaving over 500,000 residents without power across Nova Scotia. It stands as the costliest storm in Atlantic Canadian history, proving that extreme coastal impacts are governed by the thermal energy stored in our oceans. Ultimately, these real-world impacts illustrate that our modern infrastructure, from winterized power grids managed by Hydro-Quebec and BC Hydro, to northern ice roads like the Tibet to Contoido supply line, was designed around historical climatic tolerances that are currently being tested. A shortening winter road season in the Northwest Territories directly threatens northern supply chains, reducing the operational window for heavy freight transport to remote northern communities. When sea surface temperature indices jump by more than 1.5 degrees in a matter of months, the margins built into our engineering designs begin to erode. To understand how these cascading real-world impacts resolve over the coming season, we must turn to the final piece of the puzzle: the specific physical indicators and watch list metrics that will dictate whether this ocean engine settles or triggers an unprecedented wave of global weather extremes. An 81% probability of a top-tier historic ocean warming event occurring before the end of 2026 is the exact figure currently held by international meteorological agencies. That single statistic represents the final assessment of where this oceanic shift is heading. What is established beyond debate is that the Central Pacific underwent a rapid historic thermal flip between late 2025 and mid-2026, shifting the oceanic Niño index from minus 0.54 to plus 0.98 degrees Celsius in 5 overlapping seasons. It is also established that this warming erased the vertical wind shear across the Central Pacific Basin, shifting the birthplaces of tropical cyclones thousands of kilometers eastward and opening a direct corridor toward isolated regions like Hawaii, while sending high-energy atmospheric waves across North America. What remains genuinely unresolved is whether this rapid warming curve will plateau over the coming weeks or continue its upward surge, triggering a historic Super El Niño event that could fundamentally alter North American weather patterns through 2027. To know which way this system will resolve, there are three specific, checkable developments to track over the next 30 days. First, monitor the monthly Oceanic Niño Index updates released by Environment and Climate Change Canada and international monitoring partners. If the 3-month running average inside the Niño 3.4 region crosses the plus 1.5 degrees Celsius mark, the basin officially enters strong El Niño territory, locking in severe global atmospheric disruption. Second, watch the tropical cyclone track forecasts issued by the Canadian Hurricane Center in Dartmouth and the Central Pacific Hurricane Center. If future tropical storms originating in the eastern Pacific maintain their structural core past 140 degrees west longitude without rapidly decaying, it confirms that the Central Pacific thermal wall remains completely down. Third, track the seasonal jet stream advisories issued for Western Canada. If the northern branch of the Pacific Jet remains displaced northward into late autumn, it signals a high probability of severe winter drought across the prairies and elevated wildfire hazards for the 2027 season. Until one of those specific indicators shifts, the situation remains clear. The Pacific Ocean has flipped state, and the weather patterns we relied on historically no longer apply to the current atmospheric configuration. The three storms that turned across 8,000 kilometers of open ocean on a single morning in July were not isolated weather events. They were simply the first audible signals of an atmospheric engine that hasn't finished spinning up. Tell me in the comments where you are watching from tonight, and subscribe to keep following these signals.